For decades, code was committed in human-readable intervals, hours or days between updates. But as autonomous agents take over, the timeline collapses into an avalanche of commits measured in seconds. The cost of generating software syntax has effectively dropped to zero. When syntax is free, the primary bottleneck in engineering is no longer implementation logic. Today's 10x engineers are experiencing cognitive exhaustion, not from typing, but from orchestrating multiple parallel agents. The burnout comes from the mental load of managing autonomous systems, rather than manual labor. Human cognition cannot scale to match machine output. At this velocity, traditional line-by-line manual code review becomes a physical and mathematical impossibility. We have to abandon manual review in favor of a new structural framework, Agentic engineering. This framework relies on specific structural constraints: strict red-green TDD, dark factory validation, and network isolation. These methods replace syntax review with rigid behavioral constraints. We stop asking if the code looks right and start verifying that it behaves within a safe, simulated environment. Success in the zero-cost code era requires a change in perspective. We must treat agents as highly capable, inherently compromised entities that must be contained by architecture. When agents generate code without an execution environment, they act as predictive text generators. The result fractures into cascading error states because there is no ground truth to anchor the logic. We anchor this logic using red-green test-driven development. By forcing the agent to write a failing test script first, we establish a target the implementation must hit to be valid. This sequence forces the agent to establish a local execution anchor. It cannot push code outward until the red-green loop is successfully resolved. This forcing function makes the agent validate its own environment, preventing the generation of code based on hallucinated dependencies. By delegating regression testing to the agent, the engineer moves away from syntax authorship and becomes a verifier of system behavior. For enterprise deployment, we use the dark factory pattern. This is a pipeline where human engineers are forbidden from writing or even reading the implementation code. This creates a validation problem. How do you prove quality without human QA or peer review? The solution lies in simulated architecture, a method pioneered by firms like StrongDM. Because real services have rate limits, agents are used to build local Go binaries that act as mocked versions of APIs like Slack and Jira. Then, swarms of agents act as simulated employees. They fire concurrent requests into these mock endpoints 24 hours a day, mimicking months of human usage in minutes. This continuous simulated hammering uncovers edge case security failures and access bugs without any human oversight. In a dark factory, we achieve macro validation by simulating the chaos of end users at a scale humans can no longer replicate. However, even the most robust autonomous architecture has a fundamental systemic security limit that we cannot easily patch or ignore: the threat of prompt injection. Prompt injection is often confused with traditional vulnerabilities. On the top path, a SQL injection attack is neutralized by a rigid parameter shield that separates data from code. On the bottom path, a prompt injection attack passes right through the filter. Because large language models process instructions and user data on the same heuristic layer, the system cannot distinguish between the command and the payload. Large language models process data and instructions identically. This makes prompt injection a structural limitation of the architecture, rather than a bug that can be patched. To manage this, we use Simon Willison's lethal trifecta. A breach only occurs when 3 conditions meet: private data, malicious instruction, and an exfiltration channel. Mapped onto a standard digital email assistant, the external email vector provides the connection for the malicious instruction. When an external user sends a malicious instruction, the agent reaches into the private data node to pull sensitive internal documents into its active memory. Finally, the compromised agent pushes that data out through an exfiltration channel, forwarding the email to an unauthorized address. Since instruction parsing cannot be safely filtered, engineers must physically sever one of these 3 legs to ensure security. Secure deployment is a matter of network isolation, typically air-gapping the exfiltration channel, rather than relying on better prompts. This risk brings us to the normalization of deviance, a concept used to analyze the Space Shuttle Challenger disaster. Engineers knew the O-rings were unreliable, but every time a shuttle launched without a disaster, the institution felt more confident in using faulty hardware. We see the same pattern in AI deployment today. Relying on 97% effective prompt filters creates a false sense of security while ignoring the underlying flaw. Deploying unconstrained agents without severing the lethal trifecta guarantees an eventual systemic data breach. The absence of a major public exploit today is not evidence of security. It is merely the latency period before a catastrophic event occurs. This schematic shows the transition from syntax author to system orchestrator. The human is physically separated from the codebase by a strict architectural boundary. The orchestrator's role is now high-level, injecting context, reviewing QA telemetry, and managing isolation protocols. Logic is now a commodity. The high-value engineering task is building the rigid boundaries where code can safely write itself. Mastery in the agentic era is no longer about writing perfect syntax. It is about engineering the infallible constraints required to contain autonomous systems.